Welcome. I'm still working on this fusion inequality. We have an open-closed pair in a simplicial complex, and we are interested in the Betti vectors of this pair. And so we observe this inequality to understand what is happening when we are moving a simplex from a closed set to an open set. So what happens here is, in this case, we take away one maximal element. I can take a maximal element from K away and move it to the open part, and then see what happens with the Betti vectors. And so there are four possibilities which can happen algebraically. This I can prove. This is just linear algebra. What happens when you delete rows and columns of the Dirac matrix? If you take a k-dimensional simplex away, what can happen is that it affects the k-dimensional part or the k plus 1 or k minus 1 dimensional part. And Euler characteristic, of course, is conserved, so there are not many possibilities which can happen. So this is an example of a simplicial complex, and what I can do is I can take a locally maximal element away, like this one. This was the Ghostbuster case, and I move it over. So now I have an open set and I have a closed set. And what happened was that this was a one-dimensional k equal one-dimensional part. The k-dimensional part has decreased by 1, because before that, with the Betti, there were two holes, right? It's only one hole. And on the other side, what happened in the open part, I have added 1. There's another case where actually I'm changing the smaller dimensional part. For example, here in this case, I have a simplicial complex. Let me take this part away. This is a locally maximal simplex. I take it away, and what happens is I have changed the Betti number B0, because there are two components, two connected components, and so this was this case. So these are the only cases which actually can happen. So what I still have to do is to exclude these two cases. So I'm kind of documenting a little bit what I'm doing, and to see also how the process of inquiry works. So that's kind of documenting also a little bit this story, which is very, very interesting. And I have now tried a lot of different methods to look at that. So I'm chiseled from all kind of different sides. And one of the approaches, of course, is an inductive proof. That's one of the things you learn. And another proof is deformation. Deformation is kind of part of induction. So what happens when you start with something and then you take, say here, you take this away, and you have now a situation where the open set has one element. Now you can continue with this. I can take a locally maximal element away, open set, and here I have two components. So this is the next step. Now this is locally maximal, I can move this over. Now I can take again a locally maximal element, and so on. So I can transition from a larger k to a smaller k. That's what I can do here. But I can also go backwards, and that's interesting. And so I got interested this week in the process when you do this randomly. So this is a well-known thing in statistical mechanics to simulate things like in the Ising model, or kind of all kind of statistical mechanical model. Roy Glauber, who was in Arlington, he lived in Arlington, he has looked at the dynamics in the case of the Ising model. In this case, we can also look at transition Markov process. So it's a little bit simpler than I think in the Ising, because we don't have to look at some energy or anything. So what we do is, with probability, we have a kind of a threshold P0. I take it 1/2. Let's take 1/2, and then so I pick a random element in my simplicial complex. So what happens is it can be anything. It can, for example, be this, and then I also pick a random number between 0 and 1, and I see whether it's it's smaller than P0 or bigger than P0. So the rule is like that: if it's smaller than P0 and the object which we took, the simplex which we took, is in K, and if it's locally maximal in K, then I can take it away, right? Then I look whether it is smaller than P0. If it's smaller than P0 and it's in U, then I'm doing that. So I'm kind of just randomly moving between increasing k or decreasing k and increasing or decreasing u. And then I can show you an animation here what happens, so you can see what happens with this process in the long term. And what I observe is that kind of 1/2 what you would expect is kind of the threshold. If you have p0 smaller than 1/2, then it fluctuates, so that this there will be fluctuations. It never will really settle to an equilibrium, because even if you are in equilibrium, you can do something here. So you're fluctuating around, but it will have a kind of a ratio which is bigger than 1 or smaller than 1, depending on what the probability is. So that's kind of a typical question which you have in prototype question, which you have in statistical mechanics, to see what happens. There's nothing proven here about this, whether this is really the case. It's kind of reasonable to conjecture that this is happening, and then one would have to prove this, which could be considerable difficult task, especially if it would depend on the simplicial complex. So I take a random simplicial complex and do the dynamics. Also took some manifolds and see what happens. I took some complete graphs. If you take a complete complex, you can see what happens. And of course, what is interesting also is this quantity, which is how much cohomology has been created. Right? If I take a simplicity complex and I take an open set and a closed set, there are some, there is some cohomology created, which is the difference. And you look at this inequality. So, and the question is, how many particles do you create? If the proof here works, they just appear always in pairs. Okay, that's it for today.